In this lecture, we're going to talk about solving non-homogeneous linear differential equations using the method of undetermined coefficients, and specifically the annihilator approach to the method of undetermined coefficients. All right, before we can talk about the annihilator method, we need to do a little bit of review about differential operators. So remember from Calculus 1 that the differential operator denoted capital D to the n of y stands for the derivative of y. So big dy would be the first derivative of y. Big D to the second power y would be the second derivative of y. And so this is just another way that we have of writing the derivative. In addition to the form where we normally see with our differentials, dny over dxn, or y prime, y double prime, y parentheses n, right? So big D is the differential operator, and that says take the derivative of whatever it's applied to. So for example, if we have y double prime plus 4y prime plus 4y, this differential equation, we could rewrite that as d squared y to be the second derivative of y plus 4dy plus 4y equals 0. We could then factor a y out of each of those terms, so we get d squared plus 4d plus 4 times y equals 0. And then we could factor the d squared plus 4d plus 4 to be d plus 2 squared. So d plus 2 squared y equals 0 is another way of writing the differential equation in differential operator form. So the generic form for an annihilator that annihilates a polynomial is d to the n plus 1, where n is the highest degree or the degree of the polynomial. Now, if we have a function that involves a polynomial and an exponential, then the annihilator takes the form d minus alpha raised to the n plus 1, where alpha is the coefficient inside the exponential, and n is the degree of the polynomial. The final form that we could look at would be a polynomial times an exponential times a trig function. And if we have that, then the annihilator takes the form d squared minus 2 alpha d plus alpha squared plus beta squared, all raised to the n plus 1, where again alpha is the coefficient inside the exponential, beta is the coefficient inside the trig function, and n is the degree of the polynomial. So let's look at an example. We want to verify that the given operator is an annihilator for the given function. So the operator is 2d minus 1, and the function is y equals 4 e to the x over 2. So again, if this is an annihilator, then when we apply the operator to the function, so when we do 2d minus 1 times y equals 0, then when we do 2d minus 1 times y, it should equal 0. That's what would make it an annihilator. So that's what we need to show. So that's why that question mark is there. We want to see, does this equal 0? Right? So if we distribute the y, we get 2 dy minus y equals 0. So we need to figure out what the derivative of this function is. So if y is 4 e to the x over 2, then dy would be 1/2 times 4 e to the x over 2, which would be 2 e to the x over 2. So if we plug those in, we get 2 times 2e to the x over 2 minus 4e to the x over 2. So that's 4e to the x over 2 minus 4e to the x over 2. Clearly those will cancel out. We'll get 0. So this verifies, this shows that 2d minus 1 is the annihilator for the function y equals 4e to the x over 2. All right, just as a side note, the annihilator for the sum of different types of functions will be the product of the annihilator for each function. So let's use the forms that we talked about previously, along with this little tidbit, the fact that the annihilator of the sum of different types will be the product of their annihilators. Let's find some annihilators. So for our first example, we want to find the annihilator for x plus 3x e to the 6x. So this is the sum of a polynomial and a polynomial times an exponential. So using what we had the bullet point at the top here, the annihilator for this function is going to be the product of the individual annihilators. So if we can find the annihilator for x, well, x is a polynomial where n is equal to 1, so the degree is equal to 1. That means that our annihilator will be d2, or d squared. For 3x e to the 6x, so this is a polynomial times an exponential, our alpha is going to be 6. The degree of the polynomial is 1, so n will be 1. So we'll get d minus alpha raised to the n plus 1. So that'll be d minus 6 raised to the 2. And so to find the overall annihilator, we'll just multiply those two together. So the annihilator for x plus 3x e to the 6x is going to be d squared times d minus 6 quantity squared. Here's a second example. We want to find the annihilator for the function 2 minus e to the x quantity squared. Now, before we can do the annihilator for this function, we need to expand it. So if we FOIL this out, 2 minus e to the x squared is going to be 4 minus 4e to the x plus e to the 2x. Now again, this is the sum of different types of functions. So we have three functions. We have a polynomial, 4. We have 4 times e to the x, and we have e to the 2x. And since the exponentials don't have the same exponent, those are treated as two different functions. So we need to find the annihilator for each term and multiply them together. So 4 is a polynomial of degree 0. So the annihilator would be d raised to the 0 plus 1, or just d. Negative 4e to the x, our alpha is equal to 1, so we get d minus 1. And then e to the 2x, our alpha is equal to 2, so we get d minus 2. So when we multiply those three terms together, that's going to be the annihilator for this function. All right, let's do one final example where we find an annihilator. This time we have e to the negative x sine x minus e to the 2x cosine x. So again, we have two different types of terms here. The first is e to the negative x sine x, and the second is e to the 2x cosine x. Now, if the exponentials on both terms were the same, then they would just have a single annihilator. But since one of them is e to the negative x and the other is e to the 2x, we're going to have to find the annihilator of both terms and multiply together. So for our first term, e to the negative x sine of x, our alpha is negative 1, our beta is positive 1, and our n is going to be 0 because there is no there's a constant 1 there, which is a polynomial of degree 0. So we plug those values in, we get d squared minus 2 times negative 1 times d plus negative 1 squared plus 1 squared. For the second term, that e to the 2x cosine x, now our alpha is 2, our beta is 1, and our n is 0. So we get d squared minus 2 times d plus 2 squared plus 1 squared, and then raised to the 0 plus 1, or 1 power. If we simplify these, we get d squared plus 2d plus 2 times d squared minus 4d plus 5. So that product would be the annihilator of e to the negative x sine x minus e to the 2x cosine x. All right, so now that we've talked about what annihilators are, we can talk about solving ODEs using the annihilators, and specifically we're going to use the undetermined coefficients method. So to solve an ODE using the annihilator, our first step is to find the complementary solution. That's what we denote as YC, and that's the solution to the homogeneous ODE. Then we're going to apply the annihilator of the right-hand side, g of x, to both sides of the differential operator form of our ODE. Now what this is going to do is this is going to transform our ODE from a non-homogeneous equation into a homogeneous equation. Then we can find the general solution of this new homogeneous equation by finding its auxiliary function and its roots. And then what we can do is we can look at that general solution and identify the terms that were the same as our YC and whatever is left over has to be our yp. So once we have the yp, our particular solution, we're going to use the method of undetermined coefficients to figure out what the actual form of yp is. So let's do a couple of examples to illustrate how that works. Our first example, we want to solve y double prime plus 3y prime equals 4x minus 5. So again, our first step is to solve the homogeneous part. We want to find that yc. So our auxiliary equation here is going to be m squared plus 3m equals 0. If we factor that, we get m times m plus 3 equals 0. And so m is going to be 0 or negative 3. So that's going to give us a complementary solution or complementary function yc equal to c1 e to the 0 plus c2 e to the minus 3x. All right, we're going to set that aside for a few moments. We're going to rewrite our problem in differential operator form. So y double prime plus 3y prime is going to become d squared plus 3d times y. And then on the other side, that equals 4x minus 5. We denote the annihilator of the right-hand side. So 4x minus 5 is a linear equation. Its annihilator would be d squared. And then we take that annihilator and we apply it to both sides of the equation. So d squared times d squared plus 3d times y equals d squared times 4x minus 5. Now, by definition, the annihilator is going to cause the function to go to 0, so that right-hand side becomes 0, and we can factor the left-hand side out. It's going to give us d cubed times d plus 3y equals 0. Once we have the homogeneous equation, we can switch over to m's, so we can find the auxiliary function. So that's going to be m cubed times m plus 3 equals 0. And that means that the roots of our auxiliary equation are going to be 0, 0, 0, and negative 3. Using these roots, we can form the solution y equals c1 plus c2x plus c3x squared plus c4 e to the minus 3x. So this is the general solution to our problem y double prime plus 3y prime equals 4x minus 5. That means that this has both our yc, our complementary function, and our yp, our particular solution. So if we look at the terms here, we can see that that first term, c1, and that last term, c4 e to the negative 3x, those are the same as what we found for yc. So those have to be the terms from yc. That means that the terms that are left over, c2x plus c3x squared, that has to be our yp. All right, and I'm going to rewrite that using a and b just because it's a little bit easier to see when we go to solve our undetermined coefficients. So instead of c2x plus c3x squared, I'm going to write it as ax squared plus bx. All right, so we have used our annihilator to figure out what our particular solution is going to look like. Now we're going to use the method of undetermined coefficients to figure out what the a and the b is to find our particular solution. All right, so we're going to take the form of our particular solution, ax squared plus bx, and we're going to take its derivatives. So y prime would be 2ax plus b, and yp double prime would be 2a. And then we're going to plug those into our differential equation. So y double prime plus 3y prime has to equal 4x minus 5. That means 2a plus 3 times 2ax plus b has to equal 4x minus 5. We can distribute the 3 throughout the parentheses to get 2a plus 6ax plus 3b equals 4x minus 5. And then we equate our coefficients. So if we look at our x coefficients, on the left-hand side we have 6a, and on the right-hand side we have 4, so 6a has to equal 4. If we look at our constant coefficients, on the left we have 2a plus 3b, and on the right we have negative 5, so that gives us 2a plus 3b equals negative 5. So we can solve this system of equations to figure out what a and b are. If 6a equals 4, we can divide both sides by 6, and to get a equals 2/3. And then we can plug that into the second equation. So 2 times 2/3 plus 3b equals negative 5. And if we solve that for b, we'll get b equals negative 19 over 9. So that means that our particular solution is going to be 2/3 x squared minus 19 over 9x, and we put that together with our yc to form the overall solution. So y is going to be c1 plus c2 e to the minus 3x plus 2/3 x squared minus 19 over 9x. All right, let's look at another example. So this time we have y double prime plus 6y prime plus 8y equals 3e to the negative 2x plus 2x. Again, we're always going to start by solving the homogeneous part. So we find our auxiliary equation, m squared plus 6m plus 8 equals 0. We can factor this out. M plus 2 times m plus 4 equals 0. So m is going to be negative 2 and negative 4. So that means our complementary function is going to be yc equals c1 e to the negative 2x plus c2 e to the negative 4x. Again, we're going to set that aside for a little while. We're going to go back to our original equation, and we're going to rewrite it in differential operator form. So y double prime we could write as d squared y prime we could write as dy, and if we do that and factor the y out, we would get d squared plus 6d plus 8 times y equals 3e to the negative 2x plus 2x. We look at the right-hand side, 3e to the negative 2x plus 2x, and we identify the annihilator of that function. So for 3e to the negative 2x, that's an exponential. Its annihilator will be d plus 2. And 2x is a polynomial of degree 1, so its annihilator would be d squared. So we get d plus 2 times d squared as the annihilator of g of x. We apply the annihilator to both sides of our differential equation. So d squared times d plus 2 times d squared plus 6d plus 8 times y equals d squared times d plus 2 times 3e to the negative 2x plus 2x. Again, by definition, the annihilator is going to cause that right-hand side to go to 0, and we'll factor out the left-hand side. So we get d squared times d plus 2 times d plus 2 times d plus 4 equals 0. Now this is a homogeneous equation, so we could transform it into the auxiliary function, m squared times m plus 2 times m plus 2 times m plus 4 equals 0. And that means m is going to equal 0, 0, negative 2, or negative 4. So we can use those roots to form the general solution, y equals c1 plus c2x plus c3 e to the negative 2x plus c4x e to the negative 2x plus c5 e to the negative 4x. Compare this to our yc, and we see that the c3 and c5 terms take the same form as yc did, so those have to be our yc terms. That means what's left, c1 plus c2x plus c4x e to the negative 2x, those are going to have to be our yp. So we're solving y double prime plus 6y prime plus 8y equals 3e to the negative 2x plus 2x. We've identified our yp, and again, I'm going to rewrite that using a, b, and c just because it's easier to deal with. We don't have so many c's to get confused with, so I'm going to rewrite that yp form as a plus bx plus cx e to the negative 2x. To figure out a, b, and c, we'll take the derivatives of yp and plug them into the differential equation. So yp prime is going to be b plus c e to the negative 2x minus 2cx e to the negative 2x, if we use the product rule on that last term. And then yp double prime will be negative 4c e to the negative 2x plus 4cx e to the negative 2x. We'll plug these into the differential equation. So negative 4c e to the negative 2x plus 4cx e to the negative 2x, that's our y double prime, plus 6b plus 6c e to the negative 2x minus 12cx e to the negative 2x, that's our 6y prime, plus 8a plus 8bx plus 8cx e to the negative 2x, that's our 8y. And that should all equal 3e to the negative 2x plus 2x on the right-hand side. we're going to equate our coefficients. So we'll start with our e to the negative 2x coefficients. We have a negative 4c plus 6c on the left and 3 on the right. So that means 2c has to equal 3. We'll look at our x e to the negative 2x coefficients. So we have 4c minus 12 plus 8 on the left, and we have 0 on the right. And that works out, 0 equals 0, so we can keep going. We look at our constant coefficients, 6b plus 8a on the left, and there is no constant on the right, so 6b plus 8a has to equal 0. And then if we look at our x coefficients, 8b on the left and 2 on the right, means that 8b has to equal 2. So this gives us a system of 3 equations with 3 unknowns, so we can go through and solve those. If 2c equals 3, that means c has to be 3/2. And if 8b equals 2, then b has to be 1/4. Now b is 1/4. We can plug that into the middle equation, so 8a plus 6 times 1/4 has to equal 0. And we can solve that to find that a is a negative 3/16. So that means that our yp is going to be negative 3/16 plus 1/4 x plus 3/2 x e to the negative 2x. And we can put that together with our yc to form our overall solution. Y equals c1 e to the negative 2x plus c2 e to the negative 4x minus 3/16 plus 1/4 x plus 3/2 x e to the negative 2x. Let's do one final example. So this time we have y double prime plus y equals 4 cosine of x minus the sine of x. So again, we're always going to start by solving the homogeneous equation. So y double prime plus y is going to give us m squared plus 1 equals 0. If we find the roots, that means m is going to be plus or minus I. And so we'll get the yc to be c1 cosine x plus c2 sine x. All right, we're going to apply the annihilator of the right-hand side to the differential operator form of our equation. So if we have 4 cosine x minus sine x, now those both have the same alpha and beta values, so we'll have a single annihilator there. We don't have to multiply annihilators together. So our alpha is 0 because there is no exponential, and our beta is 1. So that means that the annihilator of our right-hand side is going to be d squared minus 2 times 0d plus 0 squared plus 1 squared. And if we simplify that, that's going to be d squared plus 1. All right, so we rewrite our system as we rewrite our differential equation using differential operator form. So y double prime plus y is going to be d squared plus 1 times y. And then we apply the annihilator to both sides. So d squared plus 1 times d squared plus 1 times y equals d squared plus 1 times 4 cosine x minus sine x. Now again, by definition, when we apply the annihilator to the right-hand side, it's automatically going to go to 0. So that's going to give us a homogeneous equation. And so we can transform this into the auxiliary equation by switching our d's to m's. So m squared plus 1 times m squared plus 1 has to equal 0. If we solve this for m, we're going to get m as I and negative I twice. So I, negative I, negative I. And so we can form our solution. Y equals c1 cosine x plus c2 sine x plus c3x cosine x plus c4x sine x. The first two terms were the same as our yc, so that means that the final two terms have to be our yp. We're going to rewrite those coefficients using big A and big B, so yp is ax cosine x plus bx sine x, and yp prime is going to be a cosine x minus ax sine x plus b sine x plus bx cosine x, using the product rule on both terms. And then yp double prime, we'll get negative 2a sine x minus ax cosine x plus 2b cosine x minus bx sine x. We'll plug yp prime and yp into the differential equation. So it was y double prime plus y equals 4 cosine x minus sine x. So negative 2a sine x minus ax cosine x plus 2b cosine x minus bx sine x. That's our yp double prime, plus ax cosine x plus bx sine x, that's our yp, has to equal 4 cosine x minus sine x. So we're going to equate our coefficients. If we look at our x cosine x terms, we have a negative a and a positive a, so those will cancel out. And there is nothing on the right-hand side, so we get 0 equals 0. If we look at our bx sine x terms, same thing happens. If we look at our sine terms, we have negative 2a on the left and negative 1 on the right. And if we look at our cosine terms, we have 2b on the left and 4 on the right. So we can solve this system of equations. If negative 2a equals negative 1, that means a would be 1/2. And if 2b equals 4, that means b would be 2. So we plug those values into our yp and then put it together with yc to form our overall solution. So y equals c1 cosine x plus c2 sine x plus 1/2 x cosine x plus 2x sine x.